Okay, in this video lecture, we will be seeing about the BJT small signal analysis. So we have the small signal model and what is the analysis of it. On completion, you will be able to describe the hybrid pi model, that is hybrid pi small signal model for BJT, and you will be able to explain the parameter transconductance, and you will be also able to determine the small signal parameters. So this is actually the BJT with input AC signal. So here IB, that is indicated as I, that is in a small letters, IB, IE, IC. Okay, so where it is equal to IB, that is your with represented with the uppercase letter as well as the lowercase letter. So this is a summation of IB plus IB, similarly for IE and IC. So whenever it is represented with the uppercase letter, it represents to the DC current. Whenever it is represented to the smaller case, that is your lowercase letter, it is represented to the AC current. So here this IB, IE and IC, it is the combination of DC and AC currents. So similarly, I can represent the DC voltages, AC voltages. Whenever I represent with an uppercase, it is a DC. Whenever I represent with a smaller case, then it is a AC voltage. So BJT with the small signal AC input signal. So here before that you can see in the circuit as usual, here you have an emitter current flowing, which is IE plus IE, and similarly you can see here base emitter voltage, then collector current, emitter current as well as the base current. Voltage is given to be VCC, and you have the resistors connected as usual with the base and the collector, and there is an input signal Vi given at the to the base actually, and we'll see the how it gets operated or what is the AC input signal. So small AC signal refers to the input signal VBE. That is, whenever, as I told you, whenever it is mentioned as a lowercase, then it is a AC signal. So this magnitude will be very much small than the thermal voltage VT. Okay, so the magnitude of the AC signal applied for amplification must be small so that the transistor operates in the linear region for the whole cycle of input, so which we can term it as a linear amplifier. And we should be very careful that the transistor is never driven into saturation or cutoff region. On the other hand, if the input signal is too large, okay, so in the previous case we have seen the input signal is small. Okay, if it is going to be too large, the fluctuations along the load line will drive the transistor either into saturation or the cutoff. So obviously, as we have seen in the DC load line, that is load line analysis, it will clip the input, and the amplifier is no longer, it will be a linear one. Okay, so this is the graphical analysis of the load line. So where you can see the various values are given with respect to I think you can visualize. Yes, so here we have VCE, which is equal to 0, that is at your saturation, and similarly I can give an expression for IC, and similarly the line which is indicated is a load line, and you can see a Q point over here. Okay, and this is what so at the left hand side you can see an instantaneous load line. So we have various load lines, and you can see almost in the linear segment a Q point would have been plotted. So small signal analysis. So if an AC plus DC input signal is given, the total VBE will be equal to the base emitter voltage of ECE, sorry, that is your AC plus the DC, and the collector current will now become, that is IC will be equal to IS exponential of VBE plus VBE divided by the thermal voltage, which is VT. And here IC will be equal to IC exponential of VBE by VT. For small signal, VBE is considered to be very much smaller than the VT. Okay, hence I can write IC is equal to IC into 1 plus VBE by VT, or it can be given as IC, that is your AC signal or AC current IC is equal to DC current IC plus IC VBE divided by VT. So the AC component of the collector current, obviously you can see here, it is, we know that it can be given as IC is equal to IC plus and small IC, and I can write here the AC component of the collector current is IC VBE by VT. So this GM is called as a signal transconductance, which is the ratio of collector current to the voltage across the base emitter. So this can be given as IC by VT. So it represents the slope of IC VB curve at the Q point. So small signal transconductance. This approximation implies that signal is so small that operation is restricted to almost in the linear segment of the curve, that is IC-VC curve. So you can see here there is a Q point which is plotted almost in the linear segment, and the slope is equal to the GM. Okay, and here, which we have seen previously, and IC can be, finally it can be given as GM VBE. The small signal analysis suggests that for a small signal, transistor behaves as a voltage controlled current source. The input port of the controlled current source is between the base and emitter, and output is between collector and the emitter. So coming again, other parameters, current and input resistance. So the total base current is, of course we know that, we have seen already, IB, which is equal to the AC base current plus the DC base current, and this signal component can be given by GM by beta VBE. Okay, and if I take the small signal input resistance, which is between the base and emitter, and looking into the base, I can represent this as an RN. Okay, so which will be finally equal to the thermal voltage divided by the DC base current. Okay, so similarly the emitter current can also be given, so which is with IE, which is equal to IE by VT VBE. And similarly I can represent a small signal input resistance between the base and emitter, which is looking into the emitter, I can find out what is RE. So it is again VT divided by a IE. So here VBE will be equal to IB RN, which is equal to IE RE. So similarly R pi, this is equal to beta plus 1 RE. So that's why it is called as an hybrid pi small signal model of BJT. Okay, so this model represents a transistor as a voltage controlled current source with a control voltage VBE, and it includes the input resistance looking into the base. So we have seen the previous expressions for RN, RE, so that is represented again over here. The only thing is there Rn involves a beta and Re involves alpha, right? And here the GM is given as IC by V or IC by VT. So here you can see two circuits which is of voltage controlled current source. So the other one is current controlled current source. Okay, so here the approximations for the GMVBE, which is will be equal to beta IB, and similarly IE will be equal to VBE by RE. Okay, so we know that it is a voltage controlled current source. So source is a current source, but either it could be controlled by a voltage or it could be controlled by a current. So that's what it has been shown, and in the box you can see the representations first for a voltage control and the second one is for the current control. So this includes an early effect. Okay, so here the VA represented is called as an early voltage, and this will be normally ranging from 50 volt to 100 volt. So this can be modeled as by the given expression, and we finally get an expression for IC to be IS exponential of EBE VBE by KT. So similarly we have a T model. So earlier we have seen a pi model. This is actually a T model. So in the circuit diagram, if I go back and see to the circuit diagram, you can see a shape of pi in the circuit mentioned. Okay, whereas in the next case it will be in the shape of a T, right? So this model represents a transistor as a voltage controlled current source with control voltage VBE, as well as it will include the input resistance into the looking into the emitter. So here I have represented two current sources. One is voltage control, the other one is a current control, and the approximations have been given, which is listed in the box. Okay, so finally I can say that GM VBE will be equal to alpha IE, and similarly I can write an expression for a base current IB. So when I talk about how to analyze the circuit, there is a BJT circuit using small signal model. So what are the steps and how do you analyze? Okay, so first you have to determine the DC operating point of the BJT, and in particular you have to identify what will be the collector current IC. So next you have to calculate all the small signal parameters or small signal model parameters. So transconductance GM, RN, RE for this DC operating point. Now we eliminate the DC sources. Next, eliminating the DC sources is nothing but you have to replace DC voltage source with short circuit, DC current source with a open circuit. So replacing all the capacitors by a short circuit equivalent and remove all the elements bypassed by the short circuit equivalence. So that will be the fourth step, and you have to replace the fifth step with a BJT with a small signal model. Okay, so now you analyze the resulting circuit to determine the required quantities, either voltage gain or input resistance, whatever it is. Okay, so this is like you have to identify the operating point, find what is IC, then you find out the small signal parameters, eliminate the DC source, replace all the capacitors with its equivalents, then you replace the entire BJT with the equivalent small signal model. So after that, analyze the circuit to determine the various quantities like voltage gain, input resistance. Okay, so here we have a CE voltage divider bias. So already in the biasing we have seen what is bias circuit, right? So here you can see here there will be two resistors added, one is R1 and the other one is R2. Okay, now see in the AC equivalent circuit how it has been replaced. Okay, so here you have the resistance, right? Source resistance will be there, and I have the currents flowing, and here RB, that is your base resistor, it is a parallel resistor, right? R1 and R2, so that is given as RB. Okay, R1 parallel with the R2, and I have a drop across the RE which is given by beta plus 1 RE, and this is the current source, so this is indicated with an arrow over here, and I can say here one RC is there, another one is R0, and of course the final load is there. So you can see the various currents which is mentioned and the direction of the current flow. So small signal performance parameters. Okay, so in AC analysis, we normally will be interested to find input resistance, or it is an impedance, or output resistance or an impedance, or an voltage gain. Okay, so input resistance, it is total resistance looking into the amplifier at coupling capacitor C1. It will represent the total resistance of the amplifier presented to a signal source. So the impedance, whenever you represent an impedance, obviously you have to give it with a Z. So if it is going to be input, give it as I as a suffix. So you have R1 parallel to R2, which is parallel to beta plus 1 RE. That's what given. And coming to the output resistance, so the output resistance, it is a total resistance looking into the output of the amplifier at coupling capacitor C2. Whereas the previous one, it is with the input side C1, and here it is with the output side C2. Okay, so to find the Z out, that is the output impedance, we have to set the input resistance, or the input source is set to 0, and the test source is applied at the output. Okay, so here you have an expression for Z out, which is Vx by Ix, which is actually Rc, which is parallel with the R0. Okay, so you have the test source, which is given to be Vx over here. So I can write, or I can finally say that Z out is equal to Rc, as R0 is very greater than Rc. So once it is in the denominator, obviously we can neglect that one. Voltage gain. So finally the voltage gain. So this is given by, of course, you know what will be the output voltage to the input voltage is defined to be a voltage gain, and the expressions corresponding to it is given. Of course, it is scattered. So here what are the voltages associated, what will be the output voltage, what will be the input voltage. So that is will be your voltage gain. So you can describe what is hybrid pi small signal model. Similarly, you can say what is T model. You can define transconductance. What do you mean by small AC signal? And they can solve a problem based on the parameters given for a small signal amplifier. Thank you.